you are studying the large signal equivalent circuit models with early effect. Obviously, these large signal models are introduced to work only in saturation region, right? Likewise, BJT transistors having large signal models defined for active region only. Okay, so this is the NMOS large signal model without early effect introduced in previous slides. How about PMOS without early effect? I gave this drawing to you, right? You have to draw yourself. And this is the N channel MOSFET with early effect, right? So it means you are having a output resistance. It means VDS is not constant for all value of VDS. Sorry, ID is not constant for all values of VDS in the saturation region. It actually depends that obviously VDS value should be greater than VOV, greater than or equal to VOV to be in the saturation region. But how much greater than VOV, then it will define a current in R0, and then you are having a overall effect of having different ID for different VDS in the saturation region. Okay, and we have developed this relation R0 is equal to 1 upon lambda ID or VA by ID, right? And the PMOS large signal model with early effect, source up, gate should be at the lower voltage than source, right? Obviously greater must be greater than, more negative than VT, right? VTP. And drain should be lower than S. How much lower? For saturation must be lower than VOV, right? So this is the early effect resistance to incorporate the early effect. So this is all about large signal model and all the basics of metal oxide semiconductor field effect transistors. So please remember, try to understand each and everything defined for NMOS and incontradictory defined or introduced for PMOS. And if something is not worked out in detail for PMOS, obviously the characteristics curves and others, just I show you the resemblance. Please do define that things for PMOS yourself. PMOS and NMOS both are included in your terminal examination. Okay, so this is all about the basics. Now we will analyze the DC analysis, and then followed by the AC analysis, and then discrete circuit MOSFET amplifiers similar to BJTs, right? And they are much easier. These things are much easier in MOSFET than in BJT. Why? The main thing is you don't need to have a loop equation for the gate side. Just having a single loop equation at the drain source side. And another thing is in BJT you are having different current in emitter and collector side, right? But here drain size and source size have the same current ID because there is no gate current. Okay, so let's do it in the next lecture, and in this next lecture everything will be finished. The course will be completed for the terminal examination. Thank you very much.